Hello, physics class. You should be viewing this video on Thursday, April 2nd, and I hope you all are doing well. We made it through section 1 of chapter 10, so great for that. You should have taken your quiz and gotten the grade, and we're moving on to section 2 of chapter 10, which is also the last section in chapter 10. And I want to let you know what the plan is. So obviously today is Thursday for you, and you're viewing the video right now. I'm going to go over some of the content in chapter 10.2. And then Friday, back up. Today, all you need to do is watch this video, edit your notes, update your notes, things like that, and then fill out the form that says that you watched the video. And then tomorrow, check back for the lesson plans because I'm going to have a Google form with some questions from this section. And I've made the decision not to do the math part of this session. I know that you're like really sad and crying about that right now, but I think you'll get over it. So we're not going to do any of the math. We're just going to talk about the concepts for 10.2. And then on Monday, you'll have a 10.2 quiz that'll be on the theory part from 10.2. And really, it's an open book / open note quiz because what am I going to do, right? So hopefully you'll do well on that. And then I'm just going to go ahead and do like an open book test because we need to get a test grade in for you guys as well on chapter 10. And then we'll move on. So that's what's coming up. You can see the timeline right there. So we'll be finished with chapter 10 completely after Tuesday, ready to move on to chapter 11. So let's talk for a few minutes about some of the concepts in section 10.2. And you have studied machines off and on probably your entire school career. Probably in elementary school, you started talking about simple machines. Keep in mind that a machine is a device that makes tasks easier. Like it makes work easier for the one who's operating the machine. Otherwise, why would we even have the machine, right? It would just be easier to do it yourself. And so what happens is the machine will either change the magnitude of the force or the direction of the applied force. A really quick example of when changing just the direction would be good is if you wanted to raise blinds in your house. And, it would be a really big pain if you had to climb on top of a chair and then lift them up, or climb up a little step ladder to lift up the blinds. We can simply stand, pull down on a cord, and the blinds go up. And so that's a good reason why we would want a machine to change the direction of our force. But most machines also magnify or change the magnitude of our applied force. And we pay for it though. We usually have to apply the force through a greater distance to get it to be magnified for the object. And so there's a price to be paid because you can't generate energy out of nothing. Remember, energy cannot be created or destroyed. So when we actually use a machine, we're usually having to go a greater distance to accomplish a task, but the machine is making it easier on us overall. For example, hang on 2 seconds. Let me just get rid of this. A really good quick example of this is, let's say that we were trying to load the back of a truck with a ramp. And then here's the road or the driveway, and we have a box that we need to move. So there's the box, and we want to get it into the truck bed. And so if we brought the box over, we could lift it straight up and over onto the truck. And if it's heavy, that's going to be really hard. But if we have a ramp, we can use a little bit less force to slide it up the ramp, but we're having to move it a greater distance because clearly the ramp is a lot longer than it would be just to lift it from here to here. And so, yes, we're able to use less force to accomplish this task, but we're paying for it in the sense that we're having to move the object a greater distance. And so machines are great. They help us out by allowing us to accomplish a task using yet less force on our part. But like I said, we pay a price. Similarly, a screwdriver is a simple machine, and a screwdriver is designed to embed a screw of some sort. Oh, these don't match. This is flathead, this is Phillips. But just use your imagination. Like if I wanted to embed this screw into wood, it needs to go down about that far. I would have to turn it with a screwdriver way more than that for it actually to have enough force to embed it. And so, like I said, there's a price to be paid when we use a machine, but we use it because it lets us use less force over time, so we can actually do tasks. So it's making our lives easier. And so I want to distinguish between output work and input work. Output work, or W sub O, is work done by the machine. And then input work is the work we put into the machine. Okay, it's the work that we do on a machine. And so if I want to screw a screwdriver, like I want to use this to screw a screw in a wall or whatever, my input work would be my actual turning. Like I'm having to use some torque here. Remember, that's a twisting force. And then the output work would be the screw actually going deeper and deeper into the wood. So that would be the output work when the screw's embedding into the wood. Okay, and then remember, a machine cannot receive more energy than you put into it. And so where there's always a price to be paid. Work output work can never be more than the work you put into it. And so the machine is just helping us transfer energy in an efficient way. So also related to output work and input work, we have we have effort force and resistance force. And so the effort force is the force I exert on a machine, whether it's turning this, or I'm going to pry something open with a lever, or I'm pulling down on a pulley. It's that effort that I am putting into it. And then the resistance force is the force exerted by the machine. It may be to lift an object. Okay, it may be to embed a screw into a piece of wood. Whatever that is, that's the resistance force. Okay, so we're going to talk about mechanical advantage. Hopefully this was one of the equations that you wrote down. Mechanical advantage is abbreviated capital M, capital A. And there's no unit for it because the units for the force will cancel out. But to calculate the mechanical advantage, you would divide the resistance force. Remember, that is the force exerted by the machine by the effort force. And if all you're doing is changing the direction, this should be equal to 1. Ideally, we would have a number greater than 1 to show that the machine was actually kind of taking our force and multiplying that. So we like to have mechanical advantages greater than 1. And again, I told you, I decided it was kind of a difficult decision, but without getting immediate feedback, I decided not to do the math for this section. One reason is the math for this section doesn't really build into any of our future chapters. We've already done some math in 10.1 and just trying to make this so everybody's able to move through and do this material as best as possible, and we're able to move on through the rest of the year. So another thing I wanted to talk about, I already did all that. I'm actually following along in my original notes, is ideal mechanical advantage. And remember, we have ideal gases, we have ideal strings. Well, we have ideal machines as well. And the main thing that an ideal machine is missing would be friction. And so there are no rubbing parts. There's nothing that's going to cause the machine to slow down or lose any of the amount of energy that's put into it. And so truthfully, an ideal machine does not exist. We can get closer to that by using lubricants like oils and greases and things like that so that moving parts don't rub next to each other or rub each other. But a true ideal machine does not exist. Another thing that makes a normal machine less than ideal would be sound. Sound, remember, is a type of energy. So anytime you have a machine that is making a sound, whether it's like scissors, I'm losing energy because of the sound that they're making. That's part of the energy going into an unusable form. And so sound also is a reason why we don't have ideal machines. Okay, so we can calculate the ideal mechanical advantage here, and it's abbreviated IMA. Again, no unit would be for this because the distances are canceling out, the meters or whatever you were using. You can use centimeters for both, meters for both, whatever. But it's going to be the effort distance, the distance you move the machine, divided by the distance that the machine would move the object. And a great thing, where did it go? Oh, here when I was talking about, nope, not that. When I was talking about the ramp, like this would be the effort distance. Okay, and then the other one, like if you were going straight up, this would be really the resistance difference. And so the resistance difference is usually way less than the effort distance. Okay, so keep that in mind. And I think that's all I need to say about that. And then I already talked a little bit about this, but remember, in a real machine, energy is always lost due to friction, due to sound, due to heat being produced, like from parts rubbing, thermal energy is lost. And so there are all of those types of things. And so in a real machine, we like to calculate its efficiency. And of course, the closer to 100%, the better. Only an ideal machine, which doesn't really exist, would have an efficiency of 100%. Okay, but if you have an efficiency of like 93%, that's pretty good. So the way that you calculate it is two different ways. You can do the output work divided by the input work. And so you can think about the force involved and the distance the object is moving for both of those, because remember, work equals force times distance. Or if you know your mechanical advantage and IMA, ideal mechanical advantage, you can calculate the machine in that way. And again, I decided not to do the math because none of this math builds on the other stuff. None of the other stuff that we're going to do builds on this math. And so I think it's okay to not do that. And an efficient machine would have a mechanical advantage that's really, really close to the ideal mechanical advantage. And then the next thing I want to do is talk about the different types of simple machines. Now, this should be something you're fairly familiar with, but just remember there are 6 basic types of simple machines, and they're outlined for you on page 277 in your textbook, I believe. But just to go over them very quickly, a lever. That's a bar that you can use to pivot about a point, and you can use to pry things or to move things. Like a broom is a type of lever. And you will not be required to know the different classes of levers and things like that, but there are 3 basic classes of levers. If you're interested, you're bored, you can do some more reading on that. A pulley. Most of y'all are familiar. I actually drew a pulley here. This is a very simple pulley. So you have a person. Usually you pull down on a pulley because you're down on the ground, and it will usually lift an object. A flagpole is a great example, like raising a flag on a flagpole. That's a great example of that. Wheel and axle. That's obviously on a car. We've got the wheels and they turn on the axles. The screwdriver actually acts as a wheel and axle. Like this is the part you turn would be the wheel part. This is the axle. Doorknob, another wheel and axle. If you can think about turning a doorknob and it's making it open or shut. And then inclined plane, that would be like a ramp, would be the basic one of that. A wedge. The blades of scissors are actually wedges. They're sharp on one side of it, and they come to a point. And then a screw is really this is not a screw, that's a screwdriver. A screw is really an inclined plane wrapped around a cylindrical post. And so an actual screw is obviously a screw, but so is a jar lid. You know how you twist like a mayonnaise jar lid, or even like a mountain road. You know how you would, I'm running out of space here. I think I can do, let's say that you have a mountain that you need to go up. Like you have a little house at the top of the mountain. It's your little personal hideaway there. If you needed to drive straight up this, that would be a really big problem. But you could go like here, and then you could wrap around and you can go up. And then this is obviously very much an exaggeration, but you can see how like a mountain road that just keeps kind of circling around going up would be also a form of a screw. So kind of cool if you've never thought about it like that before. So those are the 6 simple machines. And again, you can find those on page 277 if you feel like you need to review. A lot of you guys had different experiences with other science classes as you were maybe in middle school, elementary school, things like that. So Some of you may know these a little bit better than others. And then a compound machine is basically two or more simple machines that are linked together. And so scissors are a great example of a compound machine. Each arm of the scissor, I guess you could say, is a lever, and then the blades are wedges. And so there's one action. Well, I guess you could say there are two actions because I'm having to move the levers together to use them. And so this would be the fulcrum right here. That's where it's pivoting. But basically, scissors definitely count as a compound machine. Another great example, especially if you need to do yard work, is a wheelbarrow. That's going to be a wheel and an axle combined with a lever. And then a bicycle would be two wheel and axle systems linked together. And there are tons of others, but those are just a few examples. So please update your notes and then look forward to the questions tomorrow. And I think I'm going to run it like a quiz. It's not going to count as a quiz at all, but I'm going to run it like a quiz because I can set it to where you can see not only the ones you got wrong, but what the correct answer should be. So that might be really helpful in preparing for your quiz. So again, what's going to happen, I lost the thing. Oh, I erased it. Sorry. Whoops. What's going to happen is you just say that you watched the video because it's already been like 16 minutes and we're only supposed to do like 20 to 25 minute assignments. So each day for each subject. So you just go in, say, yes, I watched Mystics and Talking today and I updated my notes as needed. And then tomorrow you'll have questions on this. That will be Friday. And I'm going to run it like a quiz, but it's not a quiz. I'm just trying to get you to get your feedback so you can say, oh, if I got an 85, why did I get an 85? Like, what did I miss? And then it will do the quiz on Monday. And then I'm just going to do like an open book test on Tuesday for the whole of chapter 10, and then we'll be ready to move on. So I hope you guys are doing well. I really miss you. I hope everybody's doing okay, that no one's sick. Everybody's staying inside as much as possible because we want everyone to get back and be healthy. And I hope that you and your family are very blessed.